Greetings, my dear listeners. Today I invite you on a journey to the very edge of our understanding, to the place where the universe itself defies our expectations. For billions of years it has expanded, but in the late 20th century, scientists discovered something astonishing. It is not slowing down, as one might assume, but speeding up. What invisible force could be pushing galaxies away from each other faster and faster? We call it dark energy, a name that hides more mysteries than it reveals. Imagine the night sky, every star just a spark on the surface of an immense ocean. For a long time we thought this ocean obeyed simple laws. Where there is mass, there is gravity. Where there is gravity, there must be slowing down. The universe, it seemed, should gradually lose speed, like a stone thrown upward. But in the 1990s, two independent teams of astronomers studying Type Ia supernovae, those standard cosmic candles, saw the impossible. Instead of slowing, the cosmos was accelerating. Their discovery shook the very foundations of cosmology. Long before that, Albert Einstein introduced a cosmological constant into his equations, a term that would keep the universe stable. Later he called it his greatest blunder. And yet history, as it so often does, had its irony. The so-called blunder may have been the first glimpse of what we now call dark energy. Was Einstein right all along, only in a way he could never imagine? Let us pause for a moment and reflect. We live in a world where meaning is often hidden. Love, hope, fear, invisible, yet immensely powerful. Isn't dark energy much the same? We cannot see it directly or capture it in a laboratory, but we feel its influence in the way galaxies move, in the faint glow of distant supernovae that appear dimmer than expected, in the way the universe stretches its fabric ever wider. The story of this discovery is also the story of people, the scientists who dared to trust their data, who endured skepticism, who persisted until the evidence could no longer be ignored. For their courage, the Nobel Prize in Physics was awarded in 2011. But even then, questions remained. What exactly is dark energy? Is it the energy of empty space, the vacuum itself? Is it a new dynamic field, changing with time? Or is it a signal that our very laws of gravity are incomplete? Think of your own life. Haven't you felt invisible forces that changed your path? A chance encounter, a hidden motive, a decision that seemed small but carried enormous consequences. Dark energy is like that, the unseen hand guiding the destiny of the cosmos. And yet, here lies the most humbling truth. Nearly 68% of the entire energy content of the universe is this mysterious force. Another 27% belongs to dark matter, and only about 5% is ordinary matter. Stars, planets, people. We are but a ripple on the surface of a vast, unseen ocean. Does this not humble us? Does it not inspire us to look deeper? To tell the story of dark energy honestly, we must speak many languages. The language of physics, with its measurements of supernovae, cosmic microwave background, and large-scale structure. The language of mathematics, where equations dance between infinity and zero. The language of philosophy, which asks, what does it mean to live in a universe mostly invisible? And finally, the language of human stories. Scientists, thinkers, dreamers, who embody the search for truth. This series will take us step by step. First, we will revisit the discoveries and evidence, Hubble's diagrams, supernova surveys, cosmic microwave background satellites. Then we will explore the hypotheses: cosmological constant, quintessence, modified gravity. After that, we will imagine the scenarios for the end of time itself: the big freeze, the big rip, the big crunch. Along the way, we will weave science with meaning, data with wonder, numbers with awe. But before we go further, let us ask ourselves, why tell this story at all? Perhaps because in knowing how vast the unknown truly is, we also learn to embrace mystery in our own lives. To live on the edge of the unknown is not despair. It is creativity. It is freedom. So, my dear listeners, let us begin. We will speak with rigor but with passion, with precision but also with imagination. If the universe is accelerating, let us accelerate too, in curiosity, in wonder, in the search that defines us as human beings. Dark energy is a puzzle that has haunted physicists and philosophers alike for decades. To come closer to understanding it, we must look at the main hypotheses humanity has developed. Each of them is not just a theory. It is a worldview, a vision of the cosmos, and ultimately, of ourselves. The first hypothesis is Einstein's cosmological constant. In this view, empty space is not truly empty. It is filled with a constant amount of energy, evenly spread everywhere. This energy does not change with time or location. It is the same today as it was billions of years ago. Simple, elegant, and powerful. If this is true, then the universe's fate is sealed. It will continue expanding forever. But here lies the greatest paradox. Quantum field theory predicts a vacuum energy 1 × 10 to the 120 power greater than what we observe. This staggering mismatch is perhaps the greatest discrepancy in the history of science. How can the universe exist in such a delicate balance? The second hypothesis is quintessence. Unlike the cosmological constant, quintessence is dynamic. It can change over time, growing stronger or weaker, evolving as the universe evolves. The very word comes from ancient Greek philosophy, the fifth element beyond earth, water, air, and fire. In modern physics, it becomes a field that permeates reality, breathing life into the cosmos. If quintessence is real, the future of the universe may be far more dramatic. Dark energy could strengthen, ripping everything apart, or fade, allowing gravity to regain control. The third hypothesis is even bolder. Perhaps there is no dark energy at all. What if the acceleration of the universe is simply a sign that our understanding of gravity is incomplete? Newton's laws worked well until Einstein revealed a deeper truth. Perhaps Einstein's theory, too, is only an approximation. Modified gravity theories suggest that at cosmic scales, gravity behaves differently from what we expect. If true, this would not only rewrite cosmology, but the very foundations of physics. Philosophically, each hypothesis reshapes our perspective. If the cosmological constant rules, then the void itself is alive with energy. If quintessence exists, then the universe is a living, evolving being. If gravity is incomplete, then even our most cherished laws are provisional. In every case, dark energy challenges us to be humble, to accept that certainty may forever elude us. History teaches us that contradictions herald revolutions. The ultraviolet catastrophe gave birth to quantum mechanics. The failure of Newtonian physics in cosmic scales gave rise to relativity. Why should dark energy not lead to the next great transformation of knowledge? Let us pause for a moment and turn inward. Don't we too live with hypotheses about our own lives? We predict our futures, we build models of happiness, success, and meaning. Sometimes they fail, and we are forced to start again. Dark energy mirrors our condition, uncertain, provisional, yet still full of hope. Isn't it beautiful to think that the stars themselves wrestle with the same mysteries as we do? Scientists continue to test these theories. Telescopes, satellites, and simulations work to narrow the possibilities. And yet none has triumphed completely. We live in a rare moment when the question remains open. That is a gift. For in times of uncertainty, humanity is closest to wonder, to creativity, to the spark of discovery. In the next chapter, we will examine the evidence itself, the observations that convinced scientists the universe truly is accelerating, and that something as strange as dark energy must exist. We already know that dark energy is our best explanation for the accelerating expansion of the universe. But how do we know it truly exists? Let us dive into the evidence that has convinced scientists across the world. The first line of evidence comes from Type 1a supernovae. These spectacular stellar explosions serve as standard candles in the cosmos, because they all shine with nearly the same intrinsic brightness. By comparing their true brightness with how bright they appear from Earth, astronomers can measure their distance. In the 1990s, teams studying these supernovae discovered something shocking. Distant galaxies were fainter than expected. They weren't slowing down under gravity. They were accelerating away. This was the first undeniable clue of dark energy. The second comes from the cosmic microwave background, CMB. This ancient light, left over from the Big Bang, is like a photograph of the infant universe. Satellites like COBE, WMAP, and Planck have mapped it in astonishing detail, and the data show that the universe is flat on large scales, but only if there is a mysterious energy component pushing it apart. Without dark energy, the CMB patterns make no sense. The third piece of evidence lies in the large-scale structure of the cosmos. Galaxies are not scattered randomly. They form vast filaments, clusters, and voids. A cosmic web. Computer simulations and surveys reveal that such structures cannot evolve correctly, under gravity and visible matter alone. Once again, dark energy must be there, guiding the grand architecture of the universe. The fourth is gravitational lensing. When light from a distant galaxy passes near a massive object, it bends like light through glass. By studying these distortions, astronomers can measure how matter and energy are distributed across space. And these measurements, too, demand the presence of dark energy. What makes all of this convincing is not one observation, but their harmony. Supernovae, the CMB cosmic structure, gravitational lensing, each independent, each powerful, and yet they all point in the same direction. That convergence is what gives science confidence. But can we ever be absolutely sure? History is filled with examples of ideas once thought unquestionable, the ether, the indivisible atom, that later collapsed under better data. Perhaps dark energy is not the final answer, but only a milestone. Yet even if the theory evolves, the facts remain. The universe is accelerating. Something unseen is at work. Philosophically, this is a lesson in humility and persistence. Knowledge is never final. It is provisional, approximate, ever improving. And isn't that also how we live? We build beliefs not on one moment, but on many confirmations. We grow in confidence not from certainty, but from the chorus of experience. Scientists refine these measurements every year. New surveys like DESI and missions like Euclid sharpen our picture. Each new data point weaves into the tapestry, and with every stitch the presence of dark energy becomes clearer. The cosmos itself insists there is more here than meets the eye. In the next chapter, we will journey forward in time to imagine the possible fates of the universe, depending on how dark energy behaves. We now know that dark energy is accelerating the expansion of the universe. But what does that mean for the future of everything we know? Let us imagine the scenarios that scientists have outlined, each more dramatic than the last. The first scenario is the Big Freeze. If dark energy is truly constant, a cosmological constant, then expansion will continue forever. Galaxies will drift beyond each other's horizons. Stars will burn out and the night sky will slowly empty. Over unimaginable spans of time, even atoms may decay, leaving behind a universe cold, dark, and silent. It is a bleak vision, but also strangely poetic, the cosmos dissolving into eternal stillness. The second scenario is the Big Rip. If dark energy grows stronger over time, then one day it will overpower all other forces. First, galaxies will be torn apart. Then stars, then planets, and finally even atoms will be ripped into nothingness. Space itself will be shredded. This is the most violent fate imaginable, a cosmic apocalypse written into the equations. The third scenario is the Big Crunch. What if dark energy is not constant, but will someday reverse sign? Instead of pushing the cosmos apart, it will pull it together. The expansion will slow, stop, and then collapse. Galaxies will rush back toward each other. Stars will collide, and all matter will fall into a final, fiery singularity. Perhaps from that collapse a new Big Bang could arise. A cosmic cycle of death and rebirth. Some theorists even suggest this has happened before. And we are just one iteration of many. Philosophically, each of these visions is both science and myth. They are not mere stories, but consequences of mathematics. And yet, don't they echo humanity's oldest myths of creation and destruction? The freezing wasteland, the fiery apocalypse, the eternal cycle. Science and mythology meet at the horizon of imagination. But what do these scenarios teach us? Perhaps that endings give life meaning. If the universe will not last forever, then every moment we live is all the more precious. If the stars themselves are mortal, shouldn't we cherish our brief spark of existence? Current data suggests the Big Freeze is most likely, but science is cautious. We know too little to close the book, and that uncertainty itself is a gift, a reminder that the story of the cosmos is not finished. In the next chapter, we will turn to the tools humanity has built, the great telescopes and experiments, our eyes on the dark. To unravel the mystery of dark energy, theories alone are not enough. We need instruments capable of peering into the depths of the cosmos, tracing its expansion across billions of years. This is the age of great observatories and ambitious experiments, each designed to chase the invisible. One of the first milestones was the launch of the WMAP satellite, followed by the Planck mission. These spacecraft mapped the cosmic microwave background with breathtaking precision, revealing the fingerprint of dark energy in the earliest light of the universe. Then came the Hubble Space Telescope. Hubble not only showed us the grandeur of galaxies and nebulae, but also measured the rate of cosmic expansion with unprecedented accuracy. Its data helped prove that the universe is accelerating. Today, its successor, the James Webb Space Telescope, peers back to the age of the first stars and galaxies, pushing the frontier of cosmic history. But even Webb is only part of the story. New missions, like ESA's Euclid and NASA's Nancy Grace Roman Space Telescope, aim to map billions of galaxies, building a 3D atlas of the cosmos to chart the fingerprints of dark energy itself. On Earth, equally bold projects unfold. The Dark Energy Spectroscopic Instrument, DESI, in Arizona, uses thousands of robotic fibers to collect the light of millions of galaxies, measuring their redshifts and positions. The Vera C. Rubin Observatory in Chile will photograph the southern sky every few nights, creating a time-lapse film of the entire heavens. These datasets will be a treasure for generations, revealing how cosmic structure evolves under the pull of dark energy. Why such scale and ambition? Because dark energy does not reveal itself in a single star or galaxy. It hides in the statistics of billions, in the vast architecture of the universe. Like the wind, we cannot touch it, but we see its movement in the swaying of cosmic grass, in the bending of the light. Philosophically, this is a lesson in perspective. To understand truth, sometimes we must step back. Not a single voice, but a choir. Not a single detail, but the whole. Science, too, must see the invisible by widening its gaze. And behind every telescope are people. Engineers, programmers, technicians, astronomers. Many devote decades of their lives to instruments that will bear fruit, only for the next generation. It is a kind of faith, a devotion to knowledge itself. They build humanity's eyes, and through those eyes, the universe sees itself. So let us ask, why do we do this? Why spend billions on telescopes when the Earth has problems enough? Because to be human is to wonder, to ask questions beyond survival. And perhaps in seeking these answers, we will discover truths that transform our very future. In the next chapter, we will turn from instruments to ideas, to the theories that try to capture what dark energy might be, the vacuum, a new field, or something stranger still. We have seen the tools humanity uses to probe dark energy. Now let us step into the realm of theory, the daring ideas that try to explain what this mysterious force truly is. Here, physics brushes against philosophy, and imagination meets mathematics. The first theory is vacuum energy. In quantum mechanics, the void is not empty. Particles flicker in and out of existence, creating a restless sea of fluctuations. This sea contributes a constant background energy, precisely what Einstein's cosmological constant describes. But there is a problem. The predicted vacuum energy is staggeringly larger than what we observe, by a factor of 10 to the power of 120. This cosmological constant problem is perhaps the greatest mismatch between theory and experiment in all of science. The second theory is quintessence. Unlike vacuum energy, quintessence is not fixed. It is a dynamic field that evolves with time. It may grow stronger, fade, or even vanish. This means the universe itself could change character, its destiny written in the pulse of an unseen field. The very word quintessence recalls the ancient fifth element, a cosmic essence that binds the world together. Now, reborn in modern physics, it offers a vision of a living, breathing cosmos. The third theory is modified gravity. Instead of adding new ingredients, perhaps our recipe for the universe is wrong. Einstein's general relativity has triumphed for over a century, but maybe it breaks down at the largest scales. If so, the acceleration of the cosmos is not due to dark energy at all, but to new laws of gravity waiting to be discovered. This idea is radical but not impossible, for science has rewritten its laws before. More exotic proposals abound. Some suggest dark energy is tied to hidden dimensions of space, predicted by string theory. Others imagine it as the shadow of deeper symmetries, a property of space-time we have yet to glimpse. To many, these sound like science fiction. But recall, once, atoms and black holes were science fiction too. Philosophically, these theories remind us of a deeper truth. Knowledge is provisional. What we call truth today may be overturned tomorrow. Newton gave way to Einstein. Classical physics gave way to quantum mechanics. Might not dark energy herald the next great revolution? And isn't that how life works? We too build models of our future, only to see them collapse and be rebuilt. Our stories change, our truths evolve, and through it all we learn to grow. Science and life alike are stories of reinvention. Scientists continue to refine these theories with data, comparing predictions with reality. It is like a conversation between humanity and nature, with nature answering only yes or no. Each test, each observation is another question asked of the cosmos. In the next chapter, we will look at the partner of dark energy, dark matter. Together they make up 95% of the universe. Perhaps they are not strangers, but two faces of the same hidden truth. We have explored the main theories of dark energy. Now let us consider its mysterious partnership with dark matter. Together they dominate the cosmos, making up 95% of its content, yet both are invisible. Dark matter and dark energy are like opposing forces. Dark matter pulls, creating galaxies and structures. Dark energy pushes, stretching the fabric of space, driving galaxies apart. One binds, the other unbinds. Without both, the cosmic story would look entirely different. Scientists often describe them as painter and canvas. Dark matter paints the forms. The filaments, clusters, and galaxies. Dark energy stretches the canvas itself, expanding the arena on which the cosmic artwork unfolds. One gives shape, the other scale. Some propose that these two may not be separate at all. Perhaps they are manifestations of a single underlying field, behaving like matter in some conditions, like energy in others. This recalls the wave-particle duality of quantum physics, a single entity with two faces. Could the universe itself be built on such dualities? Philosophically, this mirrors the ancient symbol of yin and yang, opposites that struggle and yet complete one another. Dark matter as gravity's embrace, dark energy as cosmic release, harmony born of tension. Is it not beautiful that the largest truths echo the oldest wisdom? The history of science reinforces this duality. First, we discovered galaxies moved too fast. There must be unseen matter. Then we discovered the cosmos expanded too fast. There must be unseen energy. Two invisible players revealed only through their influence. It is as if the universe hides its secrets in shadow, letting us see only their outlines. Will we ever know their true nature? Perhaps. But if we do, will new mysteries take their place? Science has always advanced this way. Answers dissolve into new questions. Might dark matter and dark energy be just chapters, not the end of the story? Scientists continue to seek the link. Simulations of the cosmic web, maps of galaxies, gravitational lensing surveys. All test whether these two shadows are related. The data is still young, but hope persists that the connection may one day be revealed. And once again, the cosmos mirrors our lives. Do we not live between pull and push? The desire to hold on, the need to let go, the urge for order, the longing for freedom. Perhaps dark matter and dark energy are not just cosmic mysteries, but metaphors for the human condition. In the next chapter, we will follow dark energy's impact on the galaxies themselves and on the grand architecture of the cosmos across time. We have seen how dark matter and dark energy together shape the cosmos. Now let us focus on dark energy's direct influence on galaxies and the grand architecture of the universe. Today we observe a vast cosmic web, galaxies strung like jewels along filaments, clusters bound together, an immense void stretching between them. This structure was born from the gravity of dark matter, but its future is written by dark energy. Imagine the universe as a great elastic sheet. Dark matter tied knots into it, forming galaxies and clusters. Now dark energy pulls the sheet wider, stretching the knots apart. As time passes, galaxies drift further and further away. One day, most will vanish beyond our cosmic horizon, their light forever out of reach. Each galaxy will become an island, alone in the dark sea of space. This has profound implications. Billions of years from now, astronomers in distant civilizations may see only their own galaxy. The evidence of cosmic expansion, the grand story of the universe, will be hidden from their view. They will live in a lonely cosmos, never suspecting the vastness we now see. Philosophically, this mirrors our lives. When we are young, our world is full of connections. As we grow older, circles shrink. We are left with a few enduring ties. So too with the cosmos. Once a crowded web, it becomes sparse, leaving only the closest bonds. Scientists map the cosmic web with immense surveys. Sloan Digital Sky Survey, DESI, the Vera Rubin Observatory. These projects build 3D maps of billions of galaxies, revealing how dark energy sculpts the universe. The evidence is clear. The influence of dark energy grows stronger with time, And yet there is comfort. If dark energy had been stronger in the early cosmos, galaxies could never have formed. If weaker, everything would have collapsed too soon. We exist in a rare moment, when the balance allowed stars, planets, and life to emerge. Is that not wondrous? Each generation sees a different cosmos. For the ancients, the sky was a dome above Earth. For Galileo, it was a sea of stars. For us, it is an expanding universe. For the future, it may be an empty void. And yet the truth remains. The cosmos is never static. It is always in motion. In the next chapter, we will explore the boldest hypotheses, the radical ideas that attempt to unify dark energy with the deepest laws of nature. We have traced the evidence and theories of dark energy, but some scientists venture even further, into the boldest, most radical hypotheses, ideas that border on science fiction, yet might hold the key to cosmic truth. One proposal is the existence of a fifth force. We know 4 fundamental interactions: gravity, electromagnetism, the strong and weak nuclear forces. But what if there is another hidden force that reveals itself only across cosmic scales? In this view, dark energy is not a mystery, but the whisper of this unseen interaction. Physicists test this by searching for tiny deviations from the laws we know, small cracks that could hint at something greater. Another bold idea comes from string theory. It suggests that space has more than 3 dimensions, most of them curled up, invisible to us. Could dark energy be the effect of these hidden dimensions? If so, we live not in the full reality, but in a shadow, a projection. Understanding this would change not only physics, but philosophy itself, as radically as when Copernicus dethroned Earth from the center of the cosmos. Some even suggest that cosmic acceleration is an illusion. Imagine if we happen to live inside a vast underdense region, a cosmic void. Then the light from distant galaxies would reach us in unexpected ways, creating the illusion of acceleration. It is a daring idea, still speculative, but it reminds us, sometimes the universe fools us, and our greatest puzzles turn out to be tricks of perspective. Philosophically, these hypotheses raise profound questions. How much can we trust our perceptions? Are we prisoners of Plato's cave, seeing only shadows on the wall? Is dark energy a real substance, or just a mirror reflecting our limited tools? Scientists continue to test these possibilities. Every telescope, every simulation, every new experiment is a wager against ignorance. And though most bold ideas will fail, they still expand the frontier of imagination. Failure in science is never wasted. Each wrong path prunes the tree, bringing us closer to the truth. And in life, is it not the same? We imagine futures, some wild, some humble. Most never come true, but without them we would never grow. Our failures shape us as much as our triumphs. Dark energy, in this sense, is not only a scientific mystery, but a mirror of the human journey. In the next chapter, we will reflect more deeply. What does dark energy mean not just for physics, but for knowledge itself? What limits does it set on what we can ever know? Dark energy is not just a puzzle of physics. It is a challenge to the very idea of knowledge. It forces us to ask, can we ever truly know everything? Or will mystery always remain at the heart of reality? In the 20th century, many physicists believed the great work was nearly complete. Quantum mechanics and general relativity had explained the microscopic and the cosmic. Some thought that all that remained were details. And then came the revelations of dark matter and dark energy. Suddenly, 95% of the universe was missing from our understanding. We had been studying only a thin slice of reality. For some, this is discouraging, a reminder of our limits. But for others, it is exhilarating. Mystery is what keeps science alive. Dark energy is not a defeat but an invitation, an open door into a deeper universe. Philosophers see in this a profound lesson. Perhaps the dream of a final theory is an illusion. Perhaps knowledge is always partial, always shifting, like the horizon that recedes as we walk. Humility is built into the structure of science. And yet history reminds us, the impossible often becomes possible. Once atoms were unimaginable, once black holes unthinkable. Why should dark energy not one day be explained? Here lies the deeper question. What matters more, answers or the search itself? Even if we never uncover the true nature of dark energy, the journey of inquiry enriches us. It teaches patience, creativity, courage. It reminds us that science is not only about control, but about wonder. Scientists continue the work. They build new telescopes, run vast simulations, and write equations that might one day bridge quantum mechanics and cosmology. Many know they may not live to see the answer, and yet they labor on. That persistence, that devotion to knowledge, is itself a form of beauty. And here, too, the universe mirrors our lives. We seek meaning, knowing some questions may never be resolved. What is happiness? What is love? We may never reduce them to formulas. But in the seeking, we live more fully. Dark energy, like these mysteries, is less about closure than about inspiration. In the next chapter, we will turn to the human side of this story. The scientists themselves, for behind every telescope and equation are men and women who gave their lives to the pursuit of truth. We often speak of theories, data, and telescopes, but behind them all are people. The story of dark energy is, at its heart, the story of the scientists who pursued it. Consider Adam Rees, Brian Schmidt, and Saul Perlmutter. In the 1990s, they led rival teams hunting type Ia supernovae. Their data revealed the shocking truth: the universe is accelerating. At first, many doubted them. The idea seemed absurd, yet their persistence won out. In 2011, the three shared the Nobel Prize in Physics for their discovery. But awards are only the surface. Beneath them lie years of toil, late nights, failures, and renewed attempts. Imagine the courage it took to stand before the world and say, "The universe is not what we thought." It was not only an intellectual leap, but an act of bravery. For science is not just equations, it is the courage to doubt even what seems certain. And beyond the famous names are thousands more. Engineers who design telescopes, programmers who craft algorithms, technicians who maintain instruments in deserts and mountains, astronomers who spend night after night gazing at the stars. All of them are threads in the great fabric of discovery. Science is never the work of one, but of many. There are also the unsung heroes, those who spent decades chasing answers they never lived to see. Their data, their ideas continue to shape the present. Science is a relay race, a torch passed from one generation to the next. Dark energy is a mystery too vast for one lifetime, and yet each contribution builds the path. Philosophically, this teaches us that knowledge is not just results, but process. Not only answers, but effort. Every seeker adds to the whole, even if they do not hold the final key. And is this not true of life itself? Success is not only in endings, but in the striving along the way. What unites these scientists is curiosity, that most human of traits. To devote decades for a single glimpse of truth, to chase data through hardship, to endure skepticism and still believe. This is science as vocation, as calling, and in that devotion lies its nobility. In the next chapter we will look forward. What new missions, new telescopes, new experiments will carry this torch into the future? What might they reveal about the invisible force shaping our destiny? We have traced the discovery of dark energy, the theories, and the people behind them. Now let us turn to the future, to the projects that may finally bring us closer to understanding this great mystery. On the horizon stands ESA's Euclid mission, launched to map billions of galaxies in 3 dimensions. Euclid will allow us to trace how cosmic structure has evolved over the last 10 billion years. Its goal is clear: to measure whether dark energy is constant or whether it changes with time. NASA is preparing its own giant, the Nancy Grace Roman Space Telescope, often called Hubble's heir. Roman will chart the distribution of galaxies and study gravitational lensing with unprecedented precision. Together, Euclid and Roman will be humanity's new eyes on the accelerating cosmos. On Earth, equally ambitious projects continue. The Dark Energy Spectroscopic Instrument, DESI, is gathering spectra of tens of millions of galaxies, building the largest 3D map of the universe ever made. In Chile, the Vera C. Rubin Observatory will survey the entire southern sky every few nights, producing a living film of cosmic evolution. The data from these projects will fuel discoveries for decades to come. New ideas are also taking shape. Physicists propose ultra-precise atomic clocks to detect subtle changes that dark energy might cause. Next-generation gravitational wave observatories, like LISA, may sense ripples that reveal the nature of space-time itself. Perhaps one of these instruments will capture dark energy's fingerprint directly. Philosophically, this raises a provocative question. Are we ready for the answer? What if it tells us the universe is doomed to cold emptiness? What if it offers power we cannot control? Whatever the outcome, one truth remains. Knowledge itself is never wasted. Electricity was once a curiosity. Nuclear energy was once a dream. Each transformed the world. Might not dark energy do the same? The future of dark energy research is a story of hope. Hope that with every new telescope, every new data set, we bring the invisible into the light. Hope that humanity, restless and curious, will always reach for the unknown. In the final chapter, we will gather all that we have learned and reflect on what this cosmic mystery teaches us about the universe and about ourselves. We have reached the end of our journey. 13 chapters exploring discoveries, theories, people, and dreams, all orbiting one great enigma, dark energy. What can we say standing here at the edge of knowledge? First, that dark energy humbles us. It reminds us that 95% of the cosmos lies beyond our grasp. We are students, not masters of the universe. Second, that dark energy inspires us. It shows that the greatest forces in reality are often invisible. We cannot touch them, but we see their effects. Love, hope, meaning, they too are unseen. Yet they shape our lives as surely as dark energy shapes the stars. Third, that dark energy unites us. Its study requires thousands of people across the world, across nations and generations, working together for one purpose, the search for truth. In that cooperation lies a reflection of what humanity can be at its best. Philosophically, dark energy whispers the deepest lesson. That reality is always larger than our vision. That life is always deeper than our plans. That mystery is not a barrier but an invitation. To seek, to wonder, to imagine. To live fully in the presence of the unknown. We live in a rare and precious time. We know enough to ask great questions, and little enough to still be awed by them. This balance between knowledge and wonder is the essence of what it means to be human. So, my dear listeners, let this mystery remind you never to fear uncertainty. Let it remind you that the invisible may be the most powerful, that the cosmos is not just stars and galaxies, but an endless horizon for thought and spirit. And if the universe accelerates, let our curiosity accelerate too. Faster, farther, always reaching beyond. Greetings, my dear listeners, and thank you for walking this path with me. Ahead lie greater mysteries still, and each awaits us to uncover.